Hormone Basics. So now we're going to start a unit on the endocrine system and kind of start talking a bit about how hormones affect the body and how specifically once we move past this bit of basics about it, we'll start talking about how those hormones influence your ability to exercise, your ability to adapt to exercise, and really all the regulation that happens at that higher level. Okay, because from this point, like before this, we've basically talked about um, how the systems work and how they maybe adapt to exercise, how they accommodate exercise, how they help you do exercise. But hormones tell all those systems how to adapt and how to function, and they're kind of the controllers. They're the thing that's managing all those systems. So, all right, so let's look at hormones just very briefly. So once again, the purpose of hormones is to regulate bodily function. Okay, basically everything in your body, from your mood state to tissue growth, breakdown, your immune system function, your cardiovascular function, all this stuff is regulated to some degree by hormones, by the endocrine system. All right. So think of hormones as messengers that essentially tell your cells what to do. Okay, they're not the boss. Your brain's the boss, but they're supervisors, if you will. All right, so hormones are secreted from glands, of course. Endocrine hormones are secreted from multiple glands around the body, and here's a graphic of some of the major ones. The pituitary, thyroid, parathyroid, adrenal glands, pancreas, and the gonads. So, you guys have probably seen this before, so we can clip right along. Just look at the types of hormones. All right, there's three major types of hormones. The ones we're going to focus on are the endocrine. Endocrine hormones are characterized as not being produced anywhere near the place that they're targeted, or the cells that are going to be using the hormone. Okay, so endocrine hormones are released out in the blood and then they circulate, whereas paracrine hormones are produced locally. They're produced by a cell that's adjacent or close to the target cell. And then autocrine hormones are actually hormones that are produced by a cell for the same cell. Okay, and it's just a quick breakdown of those. Like I say, we're not really going to talk about autocrine or paracrine hormones, largely because, truth be told, we don't know a lot about these guys. It's a lot harder to measure these types of hormones because our ability to really get into a human cell and figure out what's going on inside of it is somewhat limited. Endocrine hormones, the fact that they ride in the blood, it makes it a lot easier to test for, because all you got to do is do a blood draw and you can test the hormones in it. So most of our understanding of hormones are endocrine based, but it should be noted that there are other kinds in the body. Okay, sometimes we call these trophic factors. They're just kind of local hormones. All right, so the mechanism of action. All right, so hormones, as I said, are secreted from glands. For some sort of a stimulus will tell that gland, be it the central nervous system or some sort of a feedback within the body, will tell the gland, okay, release hormone. Okay, a gland will secrete it out to the blood. It goes into circulation, and then it takes a ride in the blood. Okay, and from there, essentially all that's happening is that hormone is bouncing around inside the blood, and if it happens to come in contact with a receptor that will take it up, then it transmits some sort of a signal to that cell. It gives the cell instructions. All right. So it's important to start with the idea. We talk about target cells and the target receptor. So it's very easy to start thinking about this like it's some sort of a smart bomb, like there's some sort of a laser guidance system that's causing it to go exactly to a place. It's really not the case. All right, it's a somewhat randomized event. You have these little molecules that are floating around in the blood, and if there's enough of them, the more concentration will increase your odds of having binding occur, because it's, as I said, it's a randomized event. All right, so looking ahead here, we got there's three major types of hormones, or chemical structures of the hormone. So there's two that are non-steroidal, one that is steroid based. So like a steroid hormone is formed from cholesterol, most of the time from LDL cholesterol, the low density, quote unquote bad cholesterol you've probably heard of before. That's useful for making steroid hormones. And the other ones, the non-steroidal, are peptide, polypeptide, or protein, amino acid derived hormones. Okay, so and the chemical structure, the difference between a steroid and a non-steroidal hormone, have big implications for how they interact with cells and how they interact with the blood even. Okay, so first off, let's look at steroid hormones. All right, so steroid hormones are, as I said, they're lipid soluble because they come from cholesterol. Cholesterol, of course, is a molecule that's very similar to fat. Okay, so they have some similarities there. One of which is that they're hydrophobic. Okay, this term hydrophobic, you guys maybe have seen this before, and forgive me if you're already familiar with this, but if we look at the term here, hydro refers to water, right? Like hydroplaning. Okay, so water, phobic. Okay, so if you're phobic of something, you're afraid of it. Not like a steroid hormone is afraid of water. It just doesn't react with water very well. You guys ever heard the term they get along like oil and water? It's kind of that same instance where they don't mesh. Okay, and it has to do with the polarity of it. All right, so so they're hydrophobic. They're formed, as I said, from cholesterol. Now, the fact that they're lipid based and they're hydrophobic, it actually makes them able to pass through cell membranes. Okay, because if you guys remember back to your cellular kind of biology, the membrane of cells is a bilipid layer here, right, where you have these kind of tails, right? Oh, that was really huge. Okay, hold on. And anyway, you have this kind of lipid cellular layer, right? And they're kind of like this. Okay, I'm not going to draw it because I'm terrible at drawing. But anyway, if it's fat soluble, the fat is able to kind of just squeeze its way right through membranes. Okay, the outer membrane of a cell will accept hydrophobic things a lot more readily than it will hydrophilic things. Okay, so steroid hormones pass into the cell, and it actually binds with a receptor inside of the cell. All right, and the next slide is going to look at this a little better. Here we go. This is kind of the action of a steroid hormone. As I said, it'll interact with a cell, go right through the outer membrane, and then it comes on in, and the receptor is going to be somewhere here on the inside, close to the nucleus. Okay, so when a steroid hormone is accepted into a cell and it binds with a receptor, that hormone plus the binding plus the receptor go directly to the nucleus, and from there, it stimulates some sort of a gene expression. All right. So there's some mRNA that's released, and of course mRNA goes in the process of translation, and we get proteins that are created. Okay, so like the typical thing that we usually think about when we talk about a steroid hormone would be something like testosterone, right? So testosterone being a muscle building anabolic hormone, when it is in a muscle cell in the right instance, you're going to have that muscle start to produce extra protein because of a steroid or I'm sorry, a testosterone that came into that cell. All right. So now looking at the other type of hormone, the non-steroidal hormone, um, it's not lipid soluble, okay? Because once again, it's formed off of a protein or amino acid or peptide. They're all kind of different stages of the same thing. It's hydrophilic, okay, which means it mixes well with water, but if you have a fat layer around the cell, it means that it's going to have a hard time getting into the cell, so it doesn't. All right. Instead, for these types of hormones, they kind of have what we call a lock and key kind of relationship with the cell. All right. So there's receptors that kind of sit on the outside of a cell. All right. So in this case, you got something like this. You might have little receptors on the outside, and the hormone is gonna just whatever shape it's got, it's gonna bind here, and then you're gonna have some sort of a secondary messengers are gonna send a signal into the cell, and you're gonna get some sort of an action. Just depends on what the hormone is. All right. So looking at a better picture here, this is how that non-steroidal hormone kind of interacts with the cell. All right. So it comes here, it binds. You don't need to memorize all this stuff down here, of course, but typically once it gets into the cell, you have a cascade of reactions, okay, where there'll be substrates, there'll be protein kinases that are activated, and somehow through, depending on, I mean, in some cases there's dozens of internal steps of activation for these things, you'll get some sort of a change within the cell, all right? But just know that non-steroidal hormones don't go into the cell, they just kind of bind here at the outside, and then they cause a chain of reactions to the inside which have some sort of an effect. Alright, more look at hormones. We have anabolic and we have catabolic hormones. Alright, so here again, I want you to somewhat divorce the idea of anabolic and catabolic with strictly the idea of muscle, all right? Because I know in the common vernacular, the common way people talk about things, an anabolic hormone is one that builds muscle, right? And the catabolic hormone is one that breaks down muscle. It's not incorrect, it's just a very limited way to think about it, okay? So instead, same deal as we talked about in metabolism. Think more so that a catabolic hormone is any action which breaks down a larger thing into a smaller subgroup of things. Okay, an example of this would be the process of lipolysis. Okay, so if a hormone stimulates lipolysis, right? So lipolysis, breakdown of lipids. Okay, lysis is breakdown. Lipo is fat essentially. So breakdown of fats. So this process would be a triglyceride being broken down into three free fatty acids, right? Triglycerides, and then a glycerol head. Okay, so that's a catabolic reaction. Has nothing to do with muscle, right? It's breaking down stored fat in this case. All right, and then an anabolic action, by the same token, is not necessarily just speaking of muscle, although there are proteins, of course, that stimulate building of muscle and breakdown of muscle. Anything. It can be anything that takes smaller units and creates a bigger unit out of it. All right. So in this case, let's take lipogenesis. Same deal. Lipo dealing with fats. Genesis being creation of. Okay. So fat creation. Lipogenesis. Some hormones actually stimulate this as well. And you'll take 3 fatty acids plus a glycerol, and voila, you get a triglyceride. All right. So it's just a reversal of the other one. All right. Now, most hormones, at least the ones that we're going to talk about throughout this unit, are not strictly catabolic or anabolic. They're really a mixture of both. And we'll talk about their various actions as we go along. Okay, so let's talk about the effectiveness of hormones. Okay, so hormones, of course, can only exert any kind of a control over cells which have receptors for them. Okay, and as I've said, the binding of that hormone to the receptor is kind of a random thing. It has to do with just a certain amount of hormone floating around in solution and coming into contact or not coming into contact with its receptor. Okay, so it certainly does happen where you might have a certain amount of circulating hormone, but if it can't get to a friendly receptor or target receptor, it doesn't do anything. Okay, a good example of that would be in diabetes, and we'll talk about that in a little bit. Okay, so the things that affect the effectiveness of a hormone, or an endocrine hormone specifically, would be these things down here. Okay, so we have the concentration of hormone, and that's governed by, of course, the amount of hormone and the amount of blood, right? Because if you take a certain amount of hormone but you reduce the amount of plasma, say, in the blood, then you just increase the concentration. By the same token, if you take the same amount of hormone and you dilute the blood with more plasma, more water, then you just made the hormone less concentrated, right? And the less concentrated it is, the less chance you have of that hormone interacting with a receptor, okay? So the concentration of the hormone is paramount to whether or not it's going to exert a great effect, all right? And then the other thing is the concentration of binding sites, okay? And this is really the thing that's kind of lost when most people talk about the endocrine system. We talk about whether or not people should be able to take steroids, whether or not they should be able to take certain performance-enhancing drugs, which might be hormone-based. Some people, they might have a lot of testosterone in their blood, for example, but they might not have a lot of binding sites. And if you don't have a lot of binding sites, it doesn't really matter how much of a hormone you have if it can't find a binding site to interact with, right? So there's really two things at play here, right? How much hormone is actually there, and then the other part is how receptive, how many receptors does the cell actually have for the hormone to exert an effect. And the reason that people don't really talk about binding site too much is simply because it's, once again, a lot harder to measure. Testing hormones in the blood is pretty easy. Like I say, you just pull it out of the blood, or you can test urine sometimes, depending. But pull it out of the blood and then test it, great. But if you want to test the receptivity of the actual cells, you need to pull those cells out of the body, right? So you have to pull out muscle, which is a lot more difficult than pulling out a little bit of blood. So it's part of why you just don't hear people talk about that too much. But it is actually really important when it comes to talking about how effective a hormone actually is in the body. Okay. Now, the amount of receptors can be upregulated or downregulated, which is something we'll talk about moving forward. Now, to illustrate the idea, I always thought this is a kind of funny way to say it, but to illustrate the relationship of hormones and binding sites, I like to think about it as an 8th grade school dance, okay? And we could say, boys or girls could be the binding site of the hormone regardless. Here we're saying the hormones of the girls. Well, I think we know that's probably more the boys, but regardless. Anyway, think about it this way, okay? You got a high school dance. You got boys and girls, and at the end of the day, the idea is the two of them to dance, all right? But we have problems, all right? So things that will influence the likelihood of 8th graders dancing together, okay? If you decrease the size of the room, you increase the concentration or the relative distance between the boys and the girls, right? And if you decrease the space, I would postulate the probability of dancing increases. The probability of interaction increases, right? So that's increasing, or rather decreasing the amount of blood volume would be analogous to that, would be increasing the concentration of hormone, right? And by the same token, if you put more of them in the same room, then you have a better chance of having interaction. So that could be either boys or girls, increasing the number increases the chances of interaction. All right. So concentration of hormones determined by a number of things. Okay, so one of which is the secretion of hormone from the actual endocrine gland. Um, this is something that will vary person to person, in some cases to a great extent. Okay, um, so the rate of secretion, and the rate of secretion is influenced, or rather, it's there's an interplay between the rate of secretion and the rate of metabolism or breakdown, take up of that hormone, right? Because when a hormone comes into a binding site, it's metabolized typically, right? It binds with its receptor, and in order to get that hormone out, it doesn't just the receptor doesn't just kick the hormone back out in the bloodstream. Typically, the hormone is either consumed or somehow not viable after its interaction with the cell. Okay, so if you have a fast uptake, or maybe in this case a lot of receptivity for a hormone, then as it's being produced, it's being soaked up by cells. Okay, in that case, you might have a low concentration because you have so much receptivity that you pull it up, right? And at the same token, you might have a lot of concentration of hormone, but you don't have that great of a rate of secretion. It's just your cells aren't picking that hormone up to use it. All right, and then you have things like the transport proteins. Some hormones require transport proteins in order for them to be able to be carried in the blood. Okay, and then plasma volume. Okay, so you can actually increase the concentration of a hormone through actions like sweating. Right, sweating reduces the water volume of the body, and you can see an increased concentration of hormone that way. Or at the same token, if you drink a ton of water, you can maybe dilute the concentration of hormones. So plasma volume will influence this as well. So we talk about upregulation and downregulation of hormones. All right. So when we're talking about this, we're talking about the upregulation or downregulation of the cellular receptivity to a hormone. So sometimes what happens with a cell, it'll maybe, let's say, be inundated by a certain amount of hormone. Okay, it's binding with a hormone a lot, and like most things in the body, there will be every kind of stimulus has an effect. Okay, and if a cell is getting bombarded with a certain hormone a lot chronically, what'll typically happen is it'll decrease its receptivity to that hormone. Okay, and what that looks like is it just decreases the number of receptors. And if you have less receptors, then it means you need more hormone to elicit the same response. We see this with things like caffeine, right, which is of course not a hormone, but it mimics a hormone. A lot of drugs in the body, in general, you can't take the same amount all the time. You have to keep increasing dose in order to have the same response. And the reason for that is you have this down regulation. Okay, and an example of this would be type 2 diabetes. For those who aren't familiar with that disease process, this is essentially kind of what it looks like. Okay, you got your cell here. Okay, it's time for one of these expert drawings. All right, so we got our receptors on the outside. Okay, and these are insulin receptors. Okay, and what an insulin receptor does is it, of course, binds with insulin, and when a cell binds with one of these insulin receptors, it causes a cascade of reactions. But the net result of this is that it tells that cell to grab up glucose from the blood. Okay, it's useful, it's necessary for that to happen in order for you to be able to take up and use glucose. Great, beautiful. Now, one of the postulated reasons for why people become diabetic, or insulin resistant in this case, a type 2 diabetic, is that if you have a diet that's, say, really rich in refined sugars, the bad carbs, high glycemic index sugars, what can happen is when you eat a really sugary food, like a cake or candy bars, whatever. Um, when you eat that sort of stuff, it causes insulin to be produced at a fast rate. Okay, and when you produce a bunch of insulin, then of course that spike hits, your body pulls the glucose in. The insulin meets with these receptors, and the cell pulls in the glucose. But if it's being bombarded with insulin all the time, what starts to happen is some of these receptors start to go away. All right. So, all right. So we just lost some receptivity to insulin. All right. So here's the problem. Now, you eat the same stuff. You eat the candy bar or whatever makes your palate hungry. Oh, sorry, your palate happy. You eat your candy bar. Um, and anyway, you keep producing insulin, but that insulin is now having a diminished effect. Okay, but your blood glucose is staying high. Then what happens is your body just keeps producing more insulin because it's trying to get that blood sugar down. It doesn't want your blood sugar to be high, so you get more and more and more insulin being produced, and the cell eventually goes, all right, I can't do this all the time, so let's knock out a few more receptors. Okay, and these people will then will start becoming increasingly resistant to insulin. They're resistant to the effects of insulin, which means their blood glucose levels stay high, and there's negative consequences to that. Okay. In a truly type 2 diabetic person, this instance of having a reduced receptivity, we would probably call this person pre-diabetic, because they're not a true diabetic yet. They can still use some insulin receptivity, right? They still got a few of them, right? And these guys can still bind. But if they keep being bombarded, and if they don't change their habits, what can happen is this cell will lose all of its binding sites. Okay, so now when you eat that candy bar or whatever, you're still producing insulin. You're still producing this hormone. But the cell has said, you know what, I'm done with it. I'm over it. I don't want that insulin anymore. Okay? And these people will have a very hard time regulating, or rather lowering their blood glucose level, and that can cause damage in their neurons. You can have damage to your blood vessels, and there's broad sweeping effects throughout the body. So anyway, looking at the other side of it, upregulation in people who are type 2 diabetic. It's kind of upregulation is kind of basically the opposite, right? If you have a decrease of hormone or certain things happening within the body, sometimes cells will increase receptivity to compensate for the lower concentration of hormone. Or in the case of a type 2 diabetic changing their diet and undertaking exercise in the correct amount, then what can happen is they might start becoming more receptive to insulin. Okay, it might. I mean, this isn't in all cases. I don't want to represent this incorrectly. Okay, not all type 2 diabetics can be cured by diet and exercise. Many of them can at least be helped by it. Sometimes the disease process is cured outright. Some people don't get anything out of it. Diabetes is still, to a certain extent, a bit of an enigma as far as the exact cause and the exact treatment. But some people do see a positive benefit from changing their lifestyle. So let's just, in this case, assume that this person is having that effect. And then what they'd see is increased receptivity to insulin, and that insulin now can work the right way, and they can start pulling in glucose and utilizing it the way a normal cell would. Okay, so that would be upregulation. The receptors literally come from inside and they go back out to the outside.